And I'm back. So, part 2 of the introduction of thermochemistry. We've covered the potential energy so far. So we talked about how a bond is formed whenever my potential energy dips down. And you can see that on the chart that you have in your notes. You might not have been able to see it on the simulation as well as I'd hoped. So we have the potential energy, which is the energy stored in bonds. Now let's talk about the kinetic energy. So kinetic energy is the energy of motion. Now from a chemistry standpoint, we're talking about translational, rotational, and vibrational motion of these particles. And it's very important that we are able to look at the kinetic energy, because if we take the average kinetic energy of these particles, that is proportional to the temperature that we get. So let me talk to you or show you a simulation that kind of shows this proportional relationship that we have for average kinetic energy and temperature. And so what we have here is a container that contains neon particles, and these are in the solid state. One reason why we know that they're in a solid state is because they're really closely packed. Things that are in the solid state don't have much motion. You see we have little vibrational motion, but they're not really moving around, they're not rotating and things like that. And so this solid state has a temperature reading of 14 Kelvin. So let's see what can happen if I change the kinetic energy inside this beaker. So if I put in some energy, right? I'm putting in energy. That energy is transferring to these molecules. Since these molecules are absorbing that energy, they are now have a greater kinetic energy. You see they're moving around a lot more. They've probably also changed their phase. And we'll talk about that a little bit later on. So as these guys are changing their phase, they have more kinetic energy, and as a result, we also have a greater temperature. So what's important to know from this simulation is to realize that temperature is just a measurement of the average kinetic energy of these particles. So by being able to record temperatures, we can see if things are overall releasing energy as a system or absorbing energy as a system, and we can help calculate how much energy that is tied in with that. So this is talking about the kinetic energy aspect. So now that we have kind of an idea of the energies that we're talking about for this unit, let's talk about the law of conservation of energy. And so you've probably heard this before, the fact that energy is never created nor destroyed. It can only transfer from one system to the other. This also applies in chemistry. And so when we're talking about energy not being created or destroyed, if I put energy into a system, that is equal to the energy that the system gave off. So we're equal but opposite in the direction that we're going. So if I give off energy, then the surroundings, so if I'm the system and I'm giving off energy, the surroundings is getting that exact amount of energy that is being transferred from me to the surroundings. The only difference is that I'm releasing that energy, but the surroundings is absorbing that energy. It's absorbing and releasing the same amount. They're equal to one another, they're just opposite in direction. And in thermochem, sign conventions tell us the releasing or absorbing. Sign conventions are extremely important in this unit. So we already talked about if I have an exothermic reaction, that is a negative delta H quantity. What delta H stands for is enthalpy. Enthalpy is a measurement of the heat in terms of joules or kilojoules per mole reaction. And so we have to know, first of all, what that heat is. So heat is when two systems that come that are at different temperatures come into contact with each other, and they exchange energy in the form of heat. Now they will do this until they reach something called thermal equilibrium, and you might have watched a video on this. Thermal equilibrium is when things that are at two different temperatures will come to a happy medium, and that is when thermal equilibrium is arrived. Once they have reached thermal equilibrium, they now have the same temperature reading, or we just learned the same average kinetic energy that they have as well. So what we can do is we can take heat, which is measured in kilojoules or joules. So heat gets the sign Q. Now do not get confused with the Q that you use in electrochemistry. That Q that we used in that unit was for coulombs charge. That has no relation to what we're doing here at all. So I know that it's redundant, I know that it's confusing, but Q in this unit means heat. We measure heat in either joules or kilojoules. Now how that is different from enthalpy, which enthalpy is delta H for its symbol. This is called enthalpy. And we measure enthalpy in joules per mole reaction or kilojoules per mole reaction. And so we're going to talk about how do we convert between heat and enthalpy in our stoichiometry portion of this. It's just very important to know the difference. This has how many moles of the substance in consideration when you're doing your calculation. This does not. So what happens if I am releasing heat to the surroundings? Notice how I'm using the term system and surroundings. That's very important. The system is the reaction, whatever is happening. The surroundings is everything else. And so if I am the system and I am releasing energy to the surroundings, a couple of things are happening here. We have an exothermic reaction, which means I have a negative Q or negative heat quantity. I also have a negative delta H, a negative enthalpy sign value as well. And so I can calculate either one of those from a stoichiometric conversion, which we're going to learn later on. I just want you guys to understand this conceptually. Now, what will I witness? What will I physically see if I have an exothermic reaction? Whenever we are doing labs and things like that, there's no way we can take a little temperature probe and stick it inside these bonds and things like that. So when we take a temperature reading, we're taking a temperature reading of the surroundings. And so if I am releasing energy, what is happening to the surroundings? Your surroundings is going to get warmer. So if they get warmer, they are going to increase the temperature. And so it's always the surroundings that we are measuring whenever we have our reactions and have to indicate whether or not they're endo or exothermic. So exothermic, releasing energy, negative Q quantity, negative delta H quantity. And what do we physically see? Those surroundings will get warmer, and therefore my temperature reading that I get will increase. Well, what if I have an endothermic reaction? If I have an endothermic reaction, we get a positive Q quantity, a positive delta H quantity, and that means that the overall system has absorbed energy. Well, what do we physically see if that is the case? If our system has absorbed energy, our surroundings is what we witness, and as a result, our surroundings will get colder. And so if we were to take a measurement in lab, we will see that our temperature decreases. And so knowing this concept, knowing the sign conventions and what's happening for that is something that's very important. Now let's talk about the other things that you see as far as the terms to know. So we see enthalpy is the measurement of the exchange of energy. We talked about this as a measurement of joules per mole reaction or kilojoules per mole reaction. There are lots of different forms of enthalpy. And so all I want you to get from this is to know that we are looking at the overall reaction when we see this. So delta H of the reaction might be for any generic reaction that you have. You might have specific reactions. So this is the enthalpy of combustion. So we would be dealing with just combustion reactions. Enthalpy of formation. So we would just deal with formation of one product. Enthalpy of fusion. There's some other ones here. Let me scroll up. Enthalpy of vaporization. So just know what those mean whenever you see it, but they all are the same. It means delta H of the reaction. Now, if you look onto the second page, you also see the terms that we've talked about already: system, surroundings, endothermic, exothermic. We're going to save entropy and Gibbs free energy for later on. We're going to learn that later on in this unit. And work, we don't really talk about that in AP chemistry anymore. Standard conditions, you see this pops up again. Remember our little knot symbol? Standard conditions means you have 25 degrees Celsius. It is not STP. Remember, I'm going to say this over and over again until you guys get it in your head. STP is 0 degrees Celsius. Standard conditions is 25 degrees Celsius. Most of the stuff that we do when we work it out in lab is going to be at standard conditions because, quite frankly, 0 degrees Celsius is way too cold to work into the lab. So 25 degrees Celsius is room temperature. Those are usually our lab conditions. And there's lots of lab type things that happen during here because we have to be able to take measurements in order to quantify our heat and enthalpy that we have here. So those are a couple of different terms that we need to know. Now, make sure whenever you are expressing your delta H, remember delta G, how we said that it has to be kilojoules per mole reaction? Same idea with delta H. Delta H, we have to say either joules per mole reaction or kilojoules per mole reaction, because if we were to go through that reaction multiple times, we would get either double, triple, whatever the amount of energy. So we have to specify that as for one time that the reaction goes through. Now, on your notes, we're gonna skip through the energy and work kind of stuff. They've taken that off of the AP exam. So let's talk a little bit more about enthalpy. And so we've already discussed that enthalpy is delta H. We have, let's compare and contrast. I think I want to do that. All right, so we're going to compare and contrast enthalpy. Let me find a good marker. So we have endothermic versus exothermic. All right, so what are the differences between them? Well, we've already stated that endothermic means that the overall reaction absorbs energy. For exothermic, the overall reaction is going to release energy. What else do we know? Well, we know that when we give the signs for endo and exothermic, that endothermic gets a positive delta H sign. If we were to work with just energy in the form of heat, then we would also get a positive Q rating. Whenever we are working with exothermic reactions, that gives a sign convention of negative delta H, and if we were just working with Q, which is our heat, then that would be a negative Q quantity. Now, what happens to the surroundings? So the surroundings for endothermic, they get warmer, and so your temperature, just kidding. For endothermic, your surroundings get colder, okay? So my temperature will decrease. For my exothermic reaction, what happens to my surroundings? Exothermic is when your temperature actually increases. And so remember, when we witness things, whenever you see anything on the problem that something gets warmer or something gets colder, that is always the surroundings that we're discussing there. Now, what about endothermic versus exothermic in the form of our potential energy? Remember, for our potential energy, you see how our temperature takes care of the kinetic energy aspect? So this is our kinetic energy aspect. For our potential energy aspect, remember that's the energy stored in the bonds. If I am absorbing energy, that is my reactant side. So my reactants are going to break bonds And remember, you are absorbing energy in order to break those bonds. On this side, for potential energy, if I am exothermic, then that is referring to my product side, because in my products, I am forming new bonds. And according to that simulation, when I form new bonds, I go to a lower energy state, so therefore that energy is released as a result. Now, the very last thing I want to talk about here is what we call our potential energy diagrams. And so what we see here is a graph that is showing your potential energy on this side and the reaction progress on this side. And so we can look at these graphs and determine if our delta H is positive or negative, and therefore if the reaction is endo or exothermic. And so let's look and see how we do that. Well, right here, you will always have a starting point and an ending point. Your starting point is always referring to your reactant's energy. So this is the potential energy that your reactants have. This ending part is where my products are. So this is how much potential energy my products have. And so as the reaction progresses, whether or not my products are at a lower energy state than my reactants, or whether or not my products are at a higher energy state than my reactants, can help me determine if the reaction is endo or exothermic. So if my reactants are starting at a higher energy state than my products, what has happened as a result is I have released energy. And so if we release energy because my reactants are higher than my product's energy state, then that means that the reaction is exothermic, and therefore I get a negative delta H quantity. And so where is delta H on this graph? If I take my product's energy value and my reactant's energy value, and I say my delta H of the reaction is equal to the products minus the reactants, what type of value will I get? This is a lower number than this. So a smaller number minus a larger number will always give me a negative quantity. And so that correlates with what we stated here, that exothermic is a negative delta H quantity, and we can see that from this graph. So if I ever have to label my delta H, it is the difference between my products and my reactants energy. This right here is my delta H. And because it is a smaller number, minus, so my products, minus my reactants, smaller number, minus a larger number, it will always be a negative quantity in this case. Now, let's look at this guy here. Same idea, reactants and products, right? If I take my products, this is my delta H. If I take my delta H of the reaction and I take the products minus the reactants, it's always products minus reactants for this case, then this is a larger number minus a smaller number. What type of quantity will I get out of that? I will get a positive quantity. And so therefore, this is an endothermic graph, and it gets a positive delta H quantity as a result. So you should be able to either sketch a graph according to a delta H given, whether it's positive or negative, endo or exothermic, or you should be able to look at a graph and determine if it is endo or exothermic based upon that. Now, there's one more thing we got to talk about with these graphs while it's on there, and you watched a whole video on it, and that is called activation energy. And so what's very important to know is that activation energy is the amount of energy that it takes to actually start the reaction. So think of a gasoline engine, all right? We all drive, hopefully. And so you crank up your car, all right? Unless you have a diesel, you all have gas burners that are not diesel burners. And when you click your car over, you have a spark plug that has to ignite in order to get that gas to combust and turn your engine or whatnot. Now, I'm not a mechanic, so that's just, a very layman term version of the point I'm trying to get across. And so what that spark plug is doing is providing you energy to reach what we call the transition state. Now, at this transition state, you now have acquired enough energy in order to make my products. And so from my reactants to that transition state, that is the amount of activation energy that is needed to get that reaction to take place. Let's talk about it on this side. So here, this is my activation energy here. It's always from my reactants to the transition state. And I think it's written up there on your page. So that would be the amount of activation energy that's required for this particular reaction. All different reactions have different activation states. So you could see something that's like this. So you see how it needs a lot of activation energy for the reaction to take place. Or reactions that are like this. You see how that doesn't need very much activation energy in order for the reaction to start. But it's always my reactant to my peak. That is my activation energy. And so examples of this. The spark plugs in your automobiles, they provide activation energy for the reaction to happen. If I were to take a match and strike it onto the matchbox, that is also an example that friction from striking the match provides activation energy for that reaction to actually happen. It will not happen on its own unless I put energy into it first. Remember how we talked about our reactants? Putting in energy to break my bonds, and then my products getting energy out from forming the bonds. So that activation energy is part of that putting the energy in to be able to break those bonds. So, also what we need to know is I've talked about my reactants to this transition state. So this is for the activation energy if my reaction is going in the forward direction. Well, later on in the year, we will learn that reactions don't just go from reactants to products. They can also go from products to reactants. So if that is the case, then I can take my products to the transition state if my reaction was going the opposite way, and that would be my activation energy for the reverse reaction. So this blue is the activation energy for the forward reaction. The orange from my products to the transition state would be the activation energy for the reverse reaction if I was going from products to reactants. Same idea here, from my products to my transition state, that is my reverse activation energy. And that's only if I'm going backwards, that products to my reactants activation energy. And so this is all the kind of good stuff, conceptual stuff that we have to know dealing with enthalpy and the terms to know. What we're going to be talking about in the next couple of videos is how do we actually calculate enthalpy. And so there's all sorts of different ways, and which one you use is dependent upon what type of information you have. We are going to start with stoichiometry, then we're going to go to calorimetry, then our Hess's law, and then our bond energies. So we're going to actually hit how to calculate delta H based upon which data we're given for all of those different instances. And so I hope you guys are understanding the conceptual component, and now we're going to get ready for the mathematical approach. So I'm out. I got to walk around because my watch is dead. I'll see you later.